So let's start with the introduction. First of all, the important bit is what, where, and which kind of applications can you use this product? And this is not an R&D product. Unlike many other products from HIOKI, this is really not an R&D product. It is a product primarily used in production, in quality assurance, and in maintenance. That's kind of like really it, but all of them have their reasons. There's a reason for in all of these areas where to use this product, and we will look at that in detail and you'll find out why. But that's basically the kind of area where we're looking at. What is the competition of the HIOKI ST4030 Impulse Winding Tester? That's actually a traditional surge tester. And in a surge tester, the rule of thumb is that you need 4 wave cycles in order to make some sort of a comparison between what you sent out as an impulse and what you get back as an impulse, to then make a sort of judgment of this of what is the winding quality, whether the winding of your phase is okay or not. What you basically do, you take a voltage, you push it out into the winding, and you see what's coming back. And to make a proper analysis of that, you need 4 wave cycles. That's kind of like the rule of thumb. And now actually I'm going to start telling you a little bit about a little story about why are we doing this today. And the reason for this presentation actually is a guy called Amrik. Amrik is in the United Kingdom. Amrik has asked our UK sales partner for a demo unit of the ST4030. Amrik tested this ST4030, and the feedback that he gave to our partner, MDL in the UK, was, well, really, it can't do anything that I can't already do with my normal surge tester. Our partner in the UK was so kind to find out what is the magic surge tester that Amrik is using. And it turned out Amrik is using a €3,000 standard surge tester from a very little known company from Germany, actually. And I mean, for us, this was kind of like a blow into the face, because it's like, hang on a second, there is a €3,000 surge tester that apparently can do everything that our, well, what, €12,000 ST4030 Impulse Winding Tester can do. We have a problem with this instrument in Europe, or alternatively, or we have a problem with this instrument in general, or alternatively, maybe Amrik didn't really see the benefits of this product, which means we have obviously not explained our benefits or the benefits of this product enough. And that's actually the reason why we decided to go for this webinar. And the good thing is, of course, we asked the gentleman in the UK, well, if you're happy with your surge tester, why do you actually want to go for a new one? Why did you in the first place look for a new surge tester? And basically, he was in this company where he was working for was in the business of making coils for like hearing aids or something like that. And they are so-called damping coils. And damping coils have the big disadvantage, or well, damping coils have a magnetic area around the coil to dampen the coil effect. Now, of course, if you have a damping element in your coil, that will also have an impact when you put in a voltage, a test voltage. When you put in a test voltage, it dampens the return of the voltage, or it dampens the signal during the test time, and you only get a very limited return result. And in this case, what you can see on the screen now is a typical test curve, which you get when you have a damped coil, or basically any coil with magnetic or metallic magnetic parts around it, because the magnetic elements, they will dampen the test signal and therefore make it very difficult for a surge tester to do a signal judgment. Because as we just learned a second ago, you need about 4 wave cycles. Now I go back just very quickly. You see the 4 wave cycles with a normal wave, with a normal test signal or test procedure. And now you see the same thing with the damping coil. So in this case, it is very, very hard for a traditional surge tester to actually make a judgment if anything, if there is a damping element, which would be anything magnetic. Now, you see in this slide, I'm talking about that making a judgment with a traditional surge tester, very, very hard. Hida and I, in the preparation of this webinar, had a bit of a discussion because I am an engineer, but I've been working in sales for quite a while now. So I like to use strong words like it's impossible with a traditional surge tester to make these kind of judgments. My friend Hida is a real engineer and he works in engineering, and an engineer has a standard typical problem of saying it's impossible. Because if it's impossible, there might be somebody who has some sort of solution that makes it possible, or there might be some kind of special scenario where it's possible. So we had a long discussion about it and we settled for two varies. So it's not only very hard to do it with a traditional surge tester, we decided it's very, very hard. So HIOKI, why are we telling you this? We tell you this because the HIOKI ST4030 Impulse Winding Tester, of course, is able to make these kind of measurements. Otherwise, we wouldn't explain you that the others are not able to do so. So why is the HIOKI ST4030 able to do this? It uses a completely different judgment method, which allows to make these kind of judgments even when you don't have these 4-wave cycles available. The important bit is, why do I use the words different judgment method? The actual testing method is the same. The testing method is you use a voltage that you apply to your winding and you see basically what's coming back. You throw an impulse into the winding and something is coming back, and then you analyze what's coming back. But our interpretation model or system of what is coming back is different. It's unique. It's based on a patented solution as well, as far as I believe it is. Yes. And so from that point of view, we have a unique and a different approach, which you cannot do with a normal, which allows us to do things that a normal surge tester can't do. I'm looking at Hida to see whether I can make the very, very hard to. It's not possible. So for me as well to understand the ST4030 measurement principle is something which I had to kind of like free my mind of one thing, and that's measurement units. Because if you're an engineer, typically every kind of measurement that we do, if you use a multimeter, a clamp meter, you measure power, you measure resistance, you measure voltage, you measure frequencies, whatever. In this case, it's important that you free your mind from all kinds of measurement units. Just don't think of measurement units. So we have a measurement instrument and we tell you don't think about measurement units. So what should you think of? And what you should think of instead is a pass-fail function of an oscilloscope. So this is a typical picture of a pass-fail function of an oscilloscope, where you basically say you define a pass area and everything that's inside is pass, and whenever a signal is outside of that area, you get in an oscilloscope an information, a trigger signal or whatever, or visual information. In our case, we basically do the same thing. We set an okay area, we set a pass area, and then we have windings and coils that you would test, that would then test outside of that. And because they are outside of the pass area, something is wrong with them, which typically would be some sort of a short or missing insulation or whatever. But basically the test principle is not getting a millivolt response, but it's actually already a judgment in there to say, is this good or bad? And that's the key feature of the ST4030 winding tester. So the pass-fail system of the ST4030 looks like this. This is a screenshot that I have taken. The important part is really just in your mind, don't worry about anything you see. The measurement principle is called LC-RC measurement principle. And sometimes you see LC values or RC values. Basically, forget about them. They are not relevant for what you do because every coil is different. Every amount of winding produces a different result. So when you take a different coil to make a measurement, there is no way you can compare the results, like a different coil type, not a different specimen from the same series or something like that. But if you take I don't know, a 1 millihenry coil and a 10 millihenry coil, they are two different kind of coils. So you have to expect that the results, the measurement, these RC, LC values are completely different. You can't compare them. Therefore, they are not important. They are not critical. Just forget them. That's the important bit. So we're going to go for a little live demo. We're actually going to show you how this thing works. And what we will do for that, we have, I don't know, bought, stolen, I don't know, where did we get the stator motor from? But we have basically an e-bike stator motor. Yes, e-bike. I think a previous manager of HIOKI had an e-bike, and then he figured out that all of a sudden he had to pedal manually because we stole the three-phase motor to use our tests with it. And what we have actually done, even worse, we have, because that three-phase e-bike motor was working perfectly, what we did is we broke one of the phases. So simply with the idea of being able to show you, and you can see the soldering work to break it. As you can see, we are more used to doing like SMD soldering, so the kind of solder power that we needed to actually break this. And you can see it from the soldering work. It was hard to actually break that phase. So we're going to show you what are we going to go for. First go for this one. So this is now the camera changes. I don't know if you can change the cameras as well. I'm going to show you our specimen, which is this one. And this three-phase stator motor is very, very close to this damping coil, simply because, as you can see, it has a lot of magnetic iron elements in there on the outside, on the inside, and they would basically cause the same damping effect than our friend Amrik in the UK, who experienced that with his damping coils. Actually, the damping coils are the niche product, if you want it like that. The mainstream product would be what you see now on the camera, what you see with this three-phase stator motor. This would be an absolutely typical example for what we do. So what I'm going to do now, I'm going to go onto the webcam. Yeah, okay. So you can basically, what we're basically going to do now is we are going to measure through all three phases. We're going to measure all our three phases, and we will read the results, and then you will see that two of those phases, the reading results will be very close to each other in the pass area, and one of them will be pretty rubbish.
Yes. Now here is one half cycle.
Yeah.
Waveform.
Yeah.
And I show you actually I start the impulse. Actually, this motor shows the half cycle like this. And next, go to the other phase test.
So we're going through the phases at the moment.
Yay. Yes.
And this one is the second one. I think this is the second good one, right?
Now I start the second one.
Now you start the second one. And this one is a good one as well. So we expect it to be...
Yes. First one is a good phase.
Okay.
Reference. The second one also shows the same plot area and the same waveform shape.
Yeah. The waveform shape will, of course, always be the same, pretty much, right? When you look at three different phases, which are all the same, in the same motor.
Yeah. And next one, the last one
is the fail. This is the one where we've done the soldering work. This is the one where we've done the short circuit, where we've created a short circuit in the winding.
In the plot area, clearly outside of the area. Yeah. However, the waveform difference is very small. Yeah. It's very, very difficult to judge the pass fail. However, it clearly shows the pass fail.
So I don't know if you could actually hear Hide, because we have a microphone set up here that we only work with one microphone, which I grabbed on my side, and it's actually very difficult to move that over. we will work on the audio technology for the future. So I hope you could hear what Hina was saying. Otherwise, if you have questions, just put them in the Q&As, and we will come back to that again. I'm just going to carry on because that was really just showing you how quickly and how simple this measurement actually is. And the setup, of course, is a little bit more complicated. You need to calibrate the unit and things like that, but it is actually not rocket science. So you would have your go-through sheet, which you would go through to say, okay, let's calibrate this, let's set that. For the setup, you would need someone competent to do it, but there is absolutely no problem to integrate this into a production line, and people will just check, is it a pass or is it a fail, especially when you have the same kind of coil coming out in a production, for example, again and again. Then you expect this to be always in the same area. Okay?
To mention briefly.
Okay, cool.
Please go ahead.
Okay, so I'm stealing the video image. So shall I go? Well, hang on a second. Let me just move back for everybody who's now looking at the video. Let me just show you the setup maybe, or the measurement setup that we currently have here for a second. You know how I look, you don't need to see my face. So this is the key bit. So next slide was the live demo that we have just seen. And then one of the important things is, of course, this is the bottom information on the slide, to define a pass area. Ideally, there are good samples, which can be used as a reference. Now, in a production environment, it's no problem, of course, to have good samples and then test everything that's coming out of a production against that. In a production environment, this is actually going to be very easy to achieve. But what do you do in a service environment? What do you do when you get this kind of piece of equipment and somebody tells you, please check whether it's okay? In that case, you don't have any good samples which you can use. But that's not a problem, because what you will do, and you can see that depending on whether you have a delta or a star setup, you will see that one of the measurements you will do between UV, UW, and VW, one of those measurements will show an odd result, or the judgment will show an odd result. So either if you do a delta measurement, you will have two good ones being close to each other and one bad one. And if you have a star setup, it will be the other way around. In the star setup, you will actually have two bad ones and one good one. The important part is not, and that's why the measurement results don't matter. The result is that you will visually see that there is something wrong. Something is going to be in the fail area, and you will know that there is a problem in this thing. And then you can, of course, further investigate it. One of the cool things is that's actually something, this is something we tell you on the side, but it's really, really an important part of it. The example that we have created is just a one turn, a single short. We have only done the manipulation in the winding in just one single, between two wires. So there is only a short between two wires. And the ST4030A is so sensitive that it lets you distinguish between a one-turn short or a two-turn or N-tane short. So however many shorts you have. Every kind of short will give you a different image. And the interesting thing about that is, and now we come back to the comparison of a traditional surge tester. A surge tester is also, of course, able to use, to detect shorts. A surge tester, however, will find it very, very difficult. It's not impossible, but it's very, in this case, it's really not impossible, but it's going to be very, very difficult to actually detect just a single turn short. Multiple shorts in a row is not a problem. A surge tester will be able to detect that, but a single turn short, it's very, very difficult to detect with a normal surge tester, which means after we've been talking about production as a typical application area, this is perfect for quality assurance. Because imagine you are a manufacturer who is buying these kind of coils, who's buying stators, or who's probably buying even a complete motor, completely ready, done from the outside. And of course, your supplier is going to tell you, oh, everything's perfect, we checked it. But we all know that it's always good to have your own quality assurance that makes sure it is okay. And the ST4030 for this will give you a superb possibility to do a quality assurance check, because it is very sensitive and it can detect things that a normal surge tester, probably used by the supplier, is not able to measure. So this is really a big key part, especially for quality assurance purposes. So now we have a little bit of a quiz, but don't worry, you're muted. You don't have to answer this. The big question that we have, if you look at this screen, what is the difference between all the competitor products and ours when you look at the examples and the application pictures from the competition? What is the big difference if you look at it? And I give you the answer to it. Ours is a motor. Theirs is part of a motor, for example, the stator part, but ours is a motor with a rotor being fit into the stator. And the big difference is what your customer normally wants, and this is now the third application area, which is a service area. If you look at maintaining motors that are already built in, imagine you're in a service area and you get a motor for maintenance. What you want to do is you want to have a possibility to check, is it actually worth working on that engine or on that motor, or is it basically a reason to throw it away because there is a failure in the windings? So wouldn't it be great if you have a possibility to actually check the motor when it's still built in, and not only when it's still built in and not when it has to be disassembled? Imagine you have to disassemble a motor before you can check the electric windings. That's the case if you use a normal surge tester. With our ST4030, you don't have that necessity anymore. You can check, you can test the motor, the windings of the motor while the motor is assembled. That is the big key, unique selling point of this unit. The funny thing is, what happens when you do this test with a normal surge tester, and what happens if you move the axle of the motor? What happens if you move the rotor? If you move the rotor, your measurement signal is going to change every time. With every little bit of angle movement you're going to make with your motor, the measurement result is going to change. So with a surge tester, how on earth should you be able to say, this is a pass and this is a fail, this is a good winding or this is a bad winding? So it's absolutely not possible with a normal surge tester because of the rotation of the rotor part. With us, there is no problem, because what you can simply do, you can create a pass judgment area which basically fits. Like, it's not necessarily just a rectangular, but you actually have the possibility to create a pass judgment area like you see on the screen in the right image at the moment. You can still say this is a healthy phase, and you can make measurements by just changing turning around the motor, and then on the other side you have a defective phase. The measurement principle is exactly the same as before. The art form in this case is getting the pass judgment area right, which of course means you need to create a couple of turns of your rotor to get that. But the measurement principle is the same thing. It's a visual pass-fail method. And now comes the complicated part of this. Actually, this is not an easy part technically. This is about partial discharge, and the important part for this is we need to look at what actually is partial discharge. If you imagine a coil and you have the insulated copper windings around that coil, then these copper wires are typically, they have an insulation lacquer on top of it. And that insulation lacquer typically can withstand about 1100 volts. I think the standard, the European standard or the global standard says 1100 volts as a minimum. And basically that of course means or requires that this insulation is absolutely perfect. But as you can imagine, there is no such thing like a perfect winding. There is no such thing like anything perfect in technology. And there might be some kind of imperfections in the insulation. And if you have, sorry for that. My name is Theresa May. We had this problem in a party conference, I believe. Sorry for that. So basically, there is a possibility that you have a wire insulation which has imperfections, and it's possible that you have imperfect wire insulations meeting each other with two windings basically being next to each other, or 2 times the wire is next to each other. In this case, it's possible that when the unit and when the product is being sold and tested at the beginning, that still everything is fine. But because of the permanent usage, especially also when higher voltages are used, it might actually break this insulation. And after a certain amount of time, then you have the possibility that there is a short happening or appearing. Which of course there are some products where you really don't want to have that in precision motors, precision windings or something like that. So a typical partial discharge test is also possible with a standard surge tester. It's not a problem to do that. The challenge here is that when you do a standard surge test with a standard surge tester, and then you see these kind of tiny little spikes, which you can see in the screen now. The partial discharge, it appears as small spikes, but to analyze these spikes, you need to have big enough spikes. So otherwise it's very difficult to detect that. So what a standard surge tester would do, or what you would do with a standard surge tester, you would increase the test voltage, because the more you increase your test voltage, the bigger these small spikes become. But there is a downside. If you increase the test voltage too much, at some point you might actually damage the coil itself. So you want to check whether there is damages in a coil, but with a standard surge tester, you run the risk that you actually cause the damage in the first place, because when you use voltages that are simply too high. The good thing is, again, with the ST4030, you can achieve the same result with much lower voltages. You don't need the same high voltages than a normal standard surge tester, simply because of the sensitivity of our measurement system and of our judgment method. We just don't need that much volts to make the same kind of judgment. And if you now look at the screen, then you will see a screenshot of such a partial discharge detection option. And my first statement when I saw that, it was, Hide, that looks like an FFT from an oscilloscope. It's exactly the same thing from the way it looks. The only thing is that that's the difference. In an FFT, in the bottom, you would have a frequency domain view. In this case, it's both time domain views. So you have basically the reference signal on the top, and then you would have the findings of the spikes and the bottom highlighted. The ST4030 will set a recommended threshold. Basically, when you set up the unit, it will find what is a recommended threshold to say, here is a partial discharge issue or not, or here we experience or we can see partial discharge. There is no reason normally to change this recommended threshold. And if you can see, or what you can see here is you see a discharge spike which has been filtered by the HIOKI methods in the bottom line. And that's actually something we want to show you as well. Here's the same thing. You can see almost no difference. You can see no difference if you look at the curves On the right side where the fail is, at the very beginning, you see this overspike and the red line coming from the bottom up to the top. That's basically where a fail has been detected. And the interesting thing about this is also important to highlight, the ST4030 can be operated as a normal surge tester. You can use it if you're used to a normal surge tester view and with the values of a normal surge tester, you can use the ST4030 like a normal surge tester. And one of the things that you can see are two elements of traditional surge testing are two values. One is called flutter, FLTR, and Laplacian. These are the two values you can see at the very bottom next to the green areas, which says in and in. There's two green ins at the very bottom on both sides, usually about 1095 for the flutter value, and they are at about 1854, 1856 at the for the Laplacian value, which has been measured. So basically, both of the traditional measurement methods tell you that everything is okay with that coil or wire or DUT, but our partial discharge detection option in our measurement system actually says, hey, this is a fail. This is not okay. Okay, so you can see that a standard surge tester with standard surge testing methods, you cannot achieve this result. Next thing I would like to go for is our second live demo. What we have created, and now I'm going to move the camera again. You might want to change the camera away from the slides now to the video. I've moved away my image, so you don't need to see me.
Why don't you stop the PowerPoint?
I could stop the PowerPoint presentation. In that case, you're probably even forced to see that. I think in this case, you will see that. Okay, now you can see it in big screen. So you can see we have created, handmade by Hidekazu Mazda, handmade two discharge DUTs. It's basically copper wire that we have used. Standard twisted insulated copper wire, 0.6 millimeters in diameter, 1.1 kilovolts nominal insulation. Basically stuff you use to make your own coils. If, for example, you're a ham radio operator, then you have something like that in your basement. So this is the wire, and you can see the two specimens that we have made from that. And now I'm going to go for the camera again. So you should see the camera again, and now we're actually going to do a discharge test with both of them. We will start with the discharge of the good one, which we have created. Not we, the royal we here has created them.
Yes, I created.
And you have broken one of them, right?
Other one, yes.
Did you break it by overcharging it, by making the test in the wrong way?
No, overcharge.
Yeah, okay. So basically, to break the other one, we have done exactly what we're trying to prevent typically. We have used too much voltage. So this is the good one. And yeah, this is a good one. Hit the start button. Just to give you an image of the start button as well. Here's the start button. And you can see that we have passed this one. There is absolutely nothing wrong with this winding. And now, I'm sure you will be able to guess the result. We have tried this before.
Yes. Yes, of course. And press start. Now 30 times apply.
Okay, so you basically put a pulse on it, not just only once, but actually 30 times. And what you can see here is you can see the amount of times that actually in several occasions the installation failed, and in several occasions on this DUT you can see that there are problems in the winding. So on several times. And the cool thing is about it, I guess probably 1400 volts is what we have used this time. Yes, it's actually more than what the installation allows us to do because it's only specified until 1100. We could have done the same thing with a lower value, right?
If we test the lower voltage,
yeah,
it doesn't happen the partial discharge. So this sample calls the partial discharge from
1400. We need
more.
Or more. Okay. And the traditional surge tester would have no possibility to detect this at 1400 volts. You would need a much higher voltage for that. I think traditional surge testers usually operate 3000, 4000, 5000 volts in that area. Yeah. So from that point of view, 3000 or 4000 volts would definitely cause damage to this kind of wire because the nominal insulation is only 1100 volts. Yeah. Okay, so now I'm going to try and see if I can manage. Yeah, it looks good. Looks good. So that was our second little live demo. Basically, a quick summary for what we have told you in the last half an hour or so, which is the ST4030 is able to make measurement judgments for coils with less than 4 wave cycles. So you've seen that at the beginning. A traditional surge tester with any kind of metal environment will not be able to make a judgment, but ours does because you don't need those traditional 4 wave cycles for analysis. We are also able with the ST4030 to make measurement judgments for coils that are already built into a motor. And this is really the important, unique selling point. There is nothing around that can do that. You don't need to worry about dismantling a motor before you check the windings of it. You can do that with the ST4030. Perfect to use if you want to, if you're in a service environment. And you can detect partial discharge, which we've just seen. You can do it with much lower test voltages than what the competition can do. Partial discharge is something everyone can do. We can do it with much less voltage, and therefore we are protecting the coils because we use much less test voltage. And actually, that is it for me. Thanks very much. Thanks for comfort. Bye.